In this program, we're going to take a look at the pH of solutions. So what determines the pH of a solution depends on the ability of the ions that are present in our salt to react with water. That ability can be traced back to the parent acid or parent base from which the salt is made. Let's look at what I mean by parent acid and base. So here I have a generic chemical equation, HA representing my acid and BOH representing my base. Those combine together to create water and our ionic salt. It's the properties of this ionic salt that will determine the pH of our solution. So B+, the cation, is the conjugate acid of the parent base BOH. The A- ion in this case is the conjugate base of our parent acid HA. So we can always trace our acid back to a parent acid or base. So what determines the pH of our solution is the ability of these two ions to interact with water and produce either hydroxide or hydronium ions. Another point to always remember is the following. The stronger our parent acid or base, the weaker its conjugate. And we'll come back to that when we look at several examples. In my first example, HCl and NaOH, I have examples of strong acids and strong bases reacting, producing our salt, sodium chloride. We can trace the sodium back to our parent base, hence it's the conjugate acid of NaOH. Cl- coming from a strong parent acid, constitutes the conjugate base. Both of these come from strong parents. As a result, their conjugates are both very weak. Now what does that mean? It means that the Na+ and the Cl- hardly can react with water at all. Hence you see Nr, or no reaction. Since they don't react with water, the pH of our solution will remain neutral at 7. In my next example, I'm going to have a strong acid reacting with a weak base, ammonia. Again, let's trace back the constituents in our salt. Ammonium comes from ammonia and is the conjugate acid of ammonia. Cl-, as in the example above, is the conjugate base of HCl. This is a very weak base, as we mentioned before in the previous example, coming from a strong acid. Ammonia, on the other hand, comes from a weak base and hence constitutes a weak acid. Let's look at now the reactions of the ions with water. Ammonia, being a weak acid, is capable to react with water to produce an excess of hydronium ions. Cl, on the other hand, doesn't react with water. As a result, I have a slightly acidic solution. In my next example, I'm going to have a weak parent acid reacting with a strong base. Let's trace back where they come from. Na+ comes from our strong base and hence is a conjugate acid. Ethanoate is a conjugate base of ethanoic acid. Na going to constitute a very weak acid because it comes from a very strong parent. The ethanoate ion, on the other hand, comes from a weak acid and hence constitutes a weak base. That means that it's able to react with water, in this case, to produce hydroxide ions. So we have a basic salt. In my final example, what if both of the substances are weak? That means if we look at both parts of our salt, both of them would constitute either a weak acid or a weak base. What's then going to happen when we look at our reactions? Well, they both are capable of reacting to a small extent with water. So at first glance we might think, well, the pH will be unchanged. But what we need to look at a little bit further in this case is what are their Ka and Kb values. Here we can see that the weak acid has a larger Ka than the Kb. As a result, that reaction is going to dominate and we'll have more hydronium ions. So our last example would be slightly acidic. Questions are always welcome. Thanks for watching.